Hello, folks. Welcome to section 6.1, where we use rational exponents. Our goal for today's lesson is to rewrite expressions involving rational exponents and simplify expressions involving rational exponents. We'll even get to solve for x. So you're going to want to go ahead and grab your calculator. I know, right? Your math teacher just told you to go get your calculator for this warm-up today. While you're getting your calculator, I just wanted to give you a little bit of direction for this warm-up. You're basically typing each expression that you see in, for instance, 1, 2, 3, and 4 in your calculator to get a numeric answer. Your mission is to compare your responses, for instance, from numbers 1 and 2 and see what you get. And then again from 3 to 4 to see what you get. Your responses for 1 to 2 should be pretty similar, and from 3 to 4 should be pretty similar. So in number 5, you're observing what did you notice about your answers to 1 and 2, and then again for your answers to 3 and 4. Now, if you don't enter these things into your calculator in a certain way, you may not get the desired outcome. Remember, whenever and most of the modern calculators, the newer calculators actually do this for you. Remember when you enter a fractional, or we call it a rational exponent, in other words, when you type this guy in, you're going to want to type that in as 4, the little up caret button, and then you're going to want to quantify that rational exponent. That just means put it in parentheses. So you would say this is 4 to the 1/2 power when you go ahead and key it in. You'll need to do the same thing every time you see a rational exponent. You got to protect those things that exist in fractions, and that happens more than one time today. On number 8, it should say what is true about your answers to 6 and 7. And then numbers 9 and 10, you should observe something very similar. In the last part of today's warm-up, you're asked to draw a conclusion about fractional exponents and then their relationship to radicals. So you're trying to observe what is going on between these two things. That is your mission. So at this point in time, you're going to go ahead and pause the video and get started. All right, hopefully you met with some success. You should have noticed for number 5, yeah, you get the same answers. Same thing with 6 and 7, you do get the same answer. 9 and 10, you get the same answer. And then your conclusion's pretty straightforward. I'm hoping that you're starting to understand that the denominator in our fraction becomes the index of the radical, and that the numerator of your fraction becomes the exponent in your radical expression. Those are going to be our properties that we talk about today. So the first case we take care of is what happens when you have a 1 in the numerator of your exponent. So let's take a base a, just don't make it 0, and we're going to raise it to the 1 over n power. Well, what you noticed in your exploration today is that that's actually the same thing as taking the nth root of a to the first. And I know you know it. The big kids don't really ever write that a there. So in this regard, a to the 1 over n power is the same as the nth root of a. So let's now go ahead and put this to use by simplifying some expressions that have rational exponents. So anytime you see something raised to the 1/2 power, fun fact, that's just a square root in disguise. This 2 right here becomes the index, and this 1 right here becomes an exponent. But we don't really write it like that, we're just writing it as the square root of 16. We write that as the principal square root of 16. We're not solving for an x in this case, not yet. We're not required to have the plus or the minus. If you entered this into your calculator right now, the principal square root of 16 would output as 4. In part B, we would just write this problem as the cube root of 32. Can't leave it like that though. I know that 8 is the largest perfect cube that goes into 32. So I'm going to go ahead and simplify my cube root. This would be 2 cube roots of 4. So the first thing I did was I used the property, and then in step 2, I'm simplifying the radical. Before I jump into my a to the 1 over n equals the nth root of a property. This one, I'll notice it has a negative exponent. So I'm actually going to use my upstairs downstairs rule first to get rid of the negative exponent. And then I notice that I have the cube root of 108, just kind of chilling in my denominator there. And I am thinking right now of what perfect cubes go into 108. I think it's 27. Yep, 27 goes in 4 times. So I would simplify that. And what we get there is 1 over 3 times the cube root of 4. Now I know, we just did dividing radicals not too long ago. You're staring at that answer like Mrs. Lucas. There's a radical down there. We're not supposed to leave them. Well, for the purpose of this course, you're only responsible for getting rid of a square root in the bottom of a fraction. So you don't have to worry about rationalizing unless it's a square root on the bottom. So that's fine just the way it is. Okay, little word of caution in part D here. This 13 has an exponent, right? This is 13 to the first power. Only the x is raised to the 1/3 power. So if I go to rewrite this based on the property in the box up there, the 13 gets to hang out outside, but it's the x that gets raised to the 1/3 power there. So this will be 13 times the cube root of x for my final answer there. Okay, now to take it up a notch. Rational exponents with n in the numerator. I actually like to teach this a little bit of a different way. I actually call this the ER rule because it helps students remember which, sort of number goes there. Not that it'll put you in the emergency room. That's not what this is about. But I just say we have a raised to the exponent over our root. So that's their ER rule. In other words, that numerator, e, is going to get to stay an exponent, and that denominator, r, gets to be your root. R is for root. So e is for exponent, r is for root. So the numerator becomes an exponent, and the denominator becomes your index, or the root in your radical. So if we're setting up part A, I would actually write this as the square root of 4 cubed. And, I should also remind you that we could use our power rule on this. If we don't have a calculator, sometimes it's easier to write this as the rth root of a and then raise it to the power of e, which is what I did here in part A. So I also used my power rule from the beginning of the chapter. So this would become 2 to the 3rd, and then 2 to the 3rd is 8. Next up in part B, I got the cube root of -8, which is fine because we can have a cube root of a negative number, and then I'm going to raise that to the 4th power. The cube root of -8 is just -2, and then -2 to the 4th power actually outputs a +16. In part C, I would use my quotient rule for exponents as well, or quotient rule for radicals, depending on how you look at it. Remember, you're going to do 27 to the 2/3. And we're going to do 8 to the 2/3. So we would do the cube root of 27, and then we're going to square that, and then we'll have the cube root of 8 squared. So this will give us 3 squared on the top, and the cube root of 8 is 2, so this will give us 2 squared on the bottom. 3 squared is 9, 2 squared is 4, so 9/4 is your answer to part C. So hopefully it went okay with numbers. Wouldn't be algebra class if I didn't throw an X in it, so I am going to go ahead and practice my ER rule with with variables now. So I would simply write this as the cube root of x to the 4th. And now it makes sense why we actually divide, right? You get to finally figure out why I taught you that shortcut. 4/3 is just saying, take 4 and divide it 3 ways. So we ask ourselves, how many times does 3 go into 4? It's the division that you see. So you're getting finally the moral of the story of why we're allowed to divide those things is because radicals are actually just exponents with division in them in disguise. So it's pretty neat. So 3 goes into 4 one time. and then there's 1x left over. So it went in one time, and there was a remainder of 1. We don't really ever write those x's, so I'll leave it like that. All right, part E. This guy here is going to be the cube root of 2x. And then I'm going to raise that to the 5th power. Now you could take 2 to the 5th and then x to the 5th if you want to. But I'm going to do a little lazier. I'm going to take this 3 and divide it into the 5. So just keep in mind, you could have done this problem as the cube root of 32x to the 5th. And then, again, simplified each piece. I'm going to cut out a middleman, though. I'm going to take that 3 into the 5. I know it goes in one time. So one of the 2 x's comes out. And then, if 3 goes into 5 one time, there's still 2 left over. So this is actually 2x times the cube root of 4x squared. All right, and then problem number last as far as this set is concerned, keep in mind the 2 doesn't have a radical around it. And what I am noticing is that I could use my ER rule on the y, so this would be the 4th root of y to the 3rd. And then to use my ER rule on z to the 1/4, that would be the 4th root of z. Now upon initial scan, I can't simplify the 4th root of y to the 3rd because 4 doesn't go into 3. And I can't simplify the 4th root of z to the 1st because 4 doesn't go into 1. But do you see how they're both like indices? So I am actually allowed to use my product property on those. So I can just marry them together underneath one common radical. So this will be y to the 3rd z underneath there. And that was your ER rule with letters. Go ahead, take a few seconds here. Give yourself a little bit of independent practice. Make sure you got it. Go ahead and press pause. All right, let's see how you did. Part A, I did use my upstairs downstairs rule. And then I did my ER rule on the bottom there. We get 1/16. B is just the 4th root of 81. That's actually a perfect 4th. Remember, a shortcut way to take care of a perfect 4th is to square root and square root again. So if I square root 81, I get 9. Square root 9, I get 3. So that's how you can work that out quickly and easily. And then for part C there, sorry, let me make that a little bigger for you. Jeez, the tiniest problem ever. Okay, so I did use my ER rule first. I now know I've used the 5th root of 32 now how many times? So the 5th root of 32 is just 2. 2 squared is 4. So that's how you're going to go ahead and use your ER rule to simplify those. Another way we can use fractional or rational exponent is to actually solve for x. So we're actually going to go ahead and solve for x in 2 ways. The first way we're going to do it is we're going to go old school back to chapter 4. This is the same thing as SADMAP, where I take a square root or cube root both sides. But I can also use a rational exponent to get rid of that integer exponent chilling there too. So for number 1, I would start by undoing any subtraction or addition that I see in the problem. I can't undo this subtraction right here because it's in parentheses, so I gotta save that for the end. So I can't do these steps. The next steps I would take would be to undo any division or multiplication that I see in the problem, essentially isolating the part that had the exponent. So I would divide both sides by 2. So getting this party started, we're looking at 4x minus 1 squared equals 9. Now I got to go ahead, now that I undid the division and multiplication, I got to get rid of the e, right? Got to get rid of that exponent. And what we learned in chapter 4 is that to get rid of a squared, you square root both sides. However, don't forget your all-important plus or minus, because when we have a degree 2 polynomial, we're looking for 2 answers. This creates 2 little mini math problems for me to work out, right? So I have to do 4x minus 1 equals 3. And then I have to do 4x minus 1 equals negative 3. Add 1 to both sides. Divide both sides by 4. One of my answers is x equals 1. Add 1 to both sides for the second portion. Divide both sides by 4. Another answer I get for this problem is negative 1/2. Super important to check your work. I did check these in advance, and both actually work when you plug them back in. But that's old news. I'm going to show you a new trick. Again, the same step is to still undo any subtraction or addition that you see, and then any division or multiplication that you see. So that I'm not changing. What I'm going to change in this new way of solving this problem, giving you another tool in your math toolbox, is to get rid of the exponent. I'm going to show you something else that will get rid of an exponent. So we're going to pick up with, I'm going to do a different color here, the 4x minus 1 squared equals 9. So we're going to take it from there, assuming we just divided both sides by 2. The trick I want to show you in the second portion of this is how to get rid of that 2. Remember, you can multiply any number by its reciprocal and get 1. 3/4 times 4/3 gives you 1. It's in that way that these two things, they're called reciprocals, but they're also called multiplicative inverses because they give us the multiplicative identity of 1 when we multiply them together. So if I want to get rid of that exponent of 2, I can actually multiply 2 by 1/2, because then that gives me 4x minus 1 raised to the first power. And we're getting in the habit of like, well, if you raise something to the first power, it's actually like it's not there, so I don't need to worry about it. What we do to one side of an equation, we should always do to the other. So do you see how I raised this 2 to the 1/2 over here? Like I multiplied 2 times 1/2, I should say. I'm going to go ahead and do that on the other side. So these two things cross-canceled and kind of undid each other. And now what I have left on the other side is 9 to the 1/2 power. And what we're learning, based on today's lesson, we have a rule, so this is still 4x minus 1 on the left, that actually says, hey, that's the same as taking your square root of 9. So this does end up still giving us that square root of 9 value, or that plus or minus 3. So it's just a little bit different. It's not drastic. It's just giving you another lens with which to view the problem. So this is solving by using a rational exponent. Again, I raised both sides to the 1/2 power, which is super handy when I go ahead and I make this exponent, for instance, in a problem like 3/4. And that'll come a little later on. But yeah, again, we're going to get still 2 problems to solve. And we would still get those same 2 answers. So we would have x equals 1 and x equals negative 1/2. All right, let's try it again. It'll be something different this time because we have an odd exponent. So I don't need to worry about my plus or minus when I have an odd exponent. I only need to worry about it when I have an even exponent. That's part of your conclusion questions later. So if I'm going through the steps, again, I want to undo any subtraction or addition that I see in the problem, and I don't see any over here on the right. However, I do see some division and multiplication. I do see multiplication by a factor of 4. So if I want to get rid of that factor of 4, I just need to divide both sides by 4. And that gives me x to the 5th equals 128 divided by 4 is 32. If I'm going old school, I'm just 5th rooting both sides, right? To get rid of that x to the 5th power. And 5th root of 32, we know it is 2. And again, I don't need that plus or minus in front because there's really only one number I could raise to the 5th power and get positive 32, right? It's just 2. 2 times itself 5 times will give me 32. If I did negative 2 to the 5th power, well, hey, that gives me negative 32. But this problem called for positive 32. So this one here doesn't satisfy the equation. So it's in this regard, you don't ever need a plus or minus when your original exponent is odd, only when it's even. All right, let's do our new twist on this old method. Again, I'm going to pick up where we left off with that x to the fifth, because up until the e in SADMAP, everything is still the same. So if I want to get rid of that 5 right there, what I'm teaching you today is you could just multiply by the reciprocal. So I would do 1/5 of 5, and that would give me x to the first power. We never really write that. And what you do to one side of an equal sign, you do have to do to the other. So I have to take 32 to the 1/5, which we're learning is the same thing. What's going on in my head right now is that, yes, that is the same thing as the 5th root of 32, and that's 2. So again, not really all that different. It's just another way of writing it and another tool with which we can use to solve some harder problems a little later on. So now you get to solve for x with your rational exponents. So all in all, take a second, flip through your notes. Maybe we're learning 3 things. Well, really just 2. I feel like these 2 rules we talked about today are really one and the same. If you got the ER rule, that's really half of today's lesson. And then the other half of today's lesson is solving for x. And let's do a word problem. So we have the population of a certain animal species after t months can be modeled by the equation P equals C times 1.21 raised to the t over 3 power, where C, so we're getting some info here, C is our initial population of this animal, whatever it is. And we are supposed to find the population after 19 months if the initial population was 75. So let's make a list of the things that we know and the things that we don't. So there's 3 letters in this formula, right? I have P, I have C, and I have T. So I'm supposed to find the population after 19 months. So that means that T is 19. And it says if the initial population was 75. Well, P is just the population after some time goes by. C is actually our initial amount. And this becomes a really big idea in Chapter 7. This number in front of your exponent is always an initial value. So C is actually in this problem 75. The value I don't know, or the value I'm asked to find, is this P right here. I don't know what that is. So I'm going to go ahead and leave P where it is. The C I'll replace courtesy of substitution with 75. And T is going to be 19. And again, when you go to use your calculator, just like we did in the warm-up, you're going to want to make sure you use your parentheses with caution. So I would go ahead and use a calculator with these funky decimals. I would never give you this problem without a calculator, friends. So do not panic about that. I am entering in my calculator right now 1.21 raised to the parentheses. Probably hear my buttons clicking in the background, maybe 19 divided by 3, close my parentheses. So that value there, I got about 3.34. And then I would multiply that number there by 75. And that gives me about 250.8. I'm going to round to the nearest whole animal here. So we're looking at about 251 animals. No naked numbers, right? So that's our approximation for the population after 19 months when our initial was 75. Notice we were at some degree multiplying the initial number by a number bigger than 1. So this makes sense because if we keep multiplying by a number bigger than 1, our population grows. So that's kind of cool. All right, now you get to pause and give yourself a little bit of independent practice. All right, let's go ahead and go over that independent practice. There are your answers to part A, B, and C. And we can definitely go over these in class. D, big idea today. When do you need that plus or minus? When the original exponent is even, or if it has an even numerator, you will need to remember that we could get more than one answer. In other words, you would use your plus or minus anytime we hit these circumstances. And then good old geometry, solving for, basically in this problem you had to solve for the radius of this particular cone. Again, another word of caution, super important when you're dividing both sides by 2 pi, make sure you have parentheses around them or else your calculator is going to mess up your day. So super important. And again, if you have any questions about that, you can definitely go ahead and ask in class. I'm looking forward to seeing you.